Hi, my name is Bobby Aloysius Johnson. I'm currently a master's student at Liverpool John Moore University, and I have submitted my thesis on denoising autoencoder with temporal shift module for video anomaly detection. Let's see the details of the project. To give a background about the project, we are trying to boost the performance of surveillance cameras in the real world. So surveillance camera, they are basically high mounted cameras surveying a particular premise. So the major problems that we see in these days surveillance camera is that they are very idle, and because they are not able to process any frame they capture. Most of the time, a human person is needed to be present there and analyze whatever scenes are there. So they are like to improve that. Like many architectures have come in, and a perfect surveillance camera, what it will do is it will shortlist those very dangerous frames or anomalous frames, and it will send it to a human for further analysis. So, when considering multiple anomaly detection systems currently in the literature, we found that there are mainly three ways of training deep learning models for anomaly detection. One is through reconstruction, second one is through future frame prediction, third one is through denoising. Reconstruction means we will take an input data, the model will compress the input data, and it will reconstruct the same data. So in this compression and decompression, the model will learn what are the important features present in the video, and whatever like non-frequent or anomalous things or noise are there in the data, it will check it off. So taking the difference between reconstructed and the non-reconstructed and the input data, input video, you can get the anomaly score. Considering future frame prediction, it will take the history of like 4 or 5 previous frames, and it will predict the future frames. And in denoising, we take the input data, input video data, we will add noise to it, and the model will be trained to predict the denoised frames. So in this, the model will learn two major features. One is like what are the it will understand what are the major features of of videos in that scene or objects in that scene. Second, it will learn to reconstruct those anomalies or norm or noise in the input data. In the research, what we found is that in the preliminary research, what we found is that the denoising autoencoders or denoising models are in the very early stage of exploration, but especially in the case of temporal learning, reconstruction, and future frames are far ahead. So the aim of the project we have set is to improve the deep learning based denoising anomaly detection models to detect spatial and temporal anomalies with a stress on temporal anomalies. To achieve the same, we have set three objectives. First one, we will be exploring the state of the art temporal learning modules in the literature, and we will be implementing that particular module in deep learning. Second one, we will be creating a base model without the temporal module that we have explored. So we will get an idea of how much uplift is given by the newly added temporal module. The third objective is to compare our trained proposed model against the models in the literature. So, in the literature review, we have seen that in traditional approaches, we have around 7 methods, of which bag of word, targetry based parse encoding, HOG, and HOF. They are very good in cases where fast anomaly detections are required, because like they are very compute friendly and it can be trained and deployed very easily. But the major places where the struggle is in cases of complex scenes as in the videos having noise or shadows and things. And also, like some in many cases, multiple models are required to be used in parallel to find different kinds of anomaly in a video. For example, in case of trajectory based methods, we will need to have another spatial anomaly detector to find anomalous spatial anomalies. In deep learning based approaches, like the training is done in two parts. One is feature extraction and feature learning. The early models called cascade models, they use multiple models in parallel in different stages to find anomaly. In most of them, the features were extracted using neural networks, and the more from the features, like another Gaussian model was created to model anomaly. So an end-to-end modeling from neural network was not there. In To improve that, in later on, like end-to-end deep learning models have come into play, where both training and feature extraction are done in the same neural network. So it has improved the accuracy by a lot. But the issues faced in most of the models in those times was that they were using optical flow to train temporal learning. So, in recent times, like LSTM and 3D convolutional layer based models had been used to learn long term temporal dependencies. So, even in case of fast moving objects or objects showing long term anomalies, it can be very easily captured with high accuracy. So LSTM and 3D CNN models are currently being used in reconstruction and future frame prediction strategies, but denoising and autoencoders or denoising models have never been used with this strategy. In LSTM model, this is a sample LSTM model. We have convolution layers, but in the bottleneck layer, they have used LSTM to capture temporal dependencies. Coming to the denoising strategy, we have primarily two papers on that. One is cross-channel models, and second one is temporal averaging, which is called avid. In avid or temporal averaging, what happens is they average the consecutive frames and like feed it into like three channels of an image and use this derived image to create the model. While in cross-channel models, what happens is they train two networks to create uh, to create optical flow from raw image and the reverse. In checking the literature for the state-of-the-art temporal learning models, we have found that two-stream networks, convolutional LSTM, and 3D CNNs are very popularly used, but they have very high disadvantage that the number of training parameters are very high, and which makes them hardware unfriendly many times. But in 2019, in the latest research, it's found that a new module called temporal shift module is introduced for temporal learning, and it's found very successful in learning temporal variations at a cost of 2D CNN. So in this particular work, we have used temporal shift module for temporal learning. So normal 2D CNNs, why they are not able to learn temporal data is because consider this particular image, we have multiple frames represented by multiple colors. So in traditional 2D CNNs, like these, all the frames are independently treated or processed by the convolution network. But in temporal shift module, which is added to 2D CNN, the frames are shifted in the forward and backward temporal dimension. So when processing a particular frame, it has data from the previous and the current frames. Both the data are present in these particular layers. So when convolution is done using this particular frame, the temporal data will be learned by the model. Now, one of the major concerns is that when we shift the frames between channels between the frame, the spatial data will be affected. So in a naive approach, the shifting and the convolutions are done in the main stream of the network, but it actually spoils the spatial modeling ability. But in the base paper, they have given that if we introduce like temporal shifting in the residual channel, it will learn the temporal data without affecting the spatial data before, because we have a residual channel available.